So now we will talk about lower bounds on the extremal number. And in order to prove a lower bound on the extremal number, what do we have to do? Lower bound, to obtain lower bound, we want to lower bound on this. What we have to do is we need to construct a graph, an n vertex graph. So you might notice that if I write ptx is vertex, so n vertex graph on the m edges having no copies of f as a subgraph. If we do that, then what? This lower bound is proved. So there are some technique to obtain lower bound on the extremal number. And this technique is like very dependent on specific f that we take. Okay, there are like two different approaches. One is probabilistic approach, the other is algebraic approach. So let's just consider probabilistic approach first. So let's define the two density of H as follows. M sub 2 of H is you take you consider a subgraph H prime of H with at least 3 vertices. And then what you compute is the number of edges in this H prime minus 1 divided by the number of vertex in here divided by number of vertex minus 2. So this is some quantity called 2 density. And the reason why we write it this way will be clear from next theorem. So for any graph f, so this theorem holds for any graph f. So this statement or this proof technique is not specific to the structure of f. It works for any f as long as it has at least 2 edges. So this is a simple graph, so at least 2 edges means that it has at least 3 vertices. There exists a constant C such that for any n, there exists an F3 graph that contains no F as a subgraph on n vertices. With at least 3 times n to the minus 1 over 2 density of F achieved. In other words, the extremal number is big omega of n to the 2 minus 1 over m2f. So how do we do it? First, for this kind of statement, we can assume that n is large because this constant is our choice. So we can choose this as a small number, say 1 over billion. So 1 over billion. If we take 1 over billion, C as 1 over billion, then this statement becomes almost trivial when n is at most 1 over 10,000. If n is at most 10,000, if n is m of 10,000, then what? This number is smaller than 1. So if you just take your H with a bunch of isolated vertex, one H, and it satisfies this statement. So by taking C small, you automatically assume that the n is large, as large as you want. So anyway, so here we assume the n is large, and so we use something called alteration method. If you've taken the probability method course already, then you might be already familiar with this. So what we do is we consider a random graph, G and P, on vertex set bracket n. So whenever I write bracket n, it means the set of integers between 1 and n, which what? Say its P is 1/4 times n to the negative 1 over 2 density of F. And let F prime be a subgraph of F which attains the 2 density. The number of edges in F minus 2 divided by minus 1 divided by number of edges in F prime minus 2 is same as the 2 density of F. Then, in particular, we know that the number of edges in F prime is at least 2. Now, we consider the random variable x. Let x be the number of edges in this G and P, and what? Y be the number of distinct copies of this F prime in G and P. Okay. Now, once you have this random variable, we can apply the linearity of expectation. So again, this alteration method and then this linearity of expectation, we have dealt with it in the introduction to the graph theory, as well as the probability method course. So we can compute the expectation of x minus y and expectation of x. Each pair is included as an edge with probability p. So its expectation is p times n to 2. And the later one, what? There is n times n minus 1 times n minus the number of vertices in F prime plus 1 ways to choose the ordered tuple of which are the candidate to obtain a copy of F prime. And depending on the number of automorphism in F prime, we get this number. And as we let this P be this number, you can, and assuming n is large, this is at least like 1 over 7 times n to the 2 minus 1 over 2 density of F minus P times P to the number of edges in F prime times at least n to the number of vertices in F prime. But what do you know? Because of this, what? The 1 over 7 times n to the, we know this equality. So if you apply that, then what do you get? 2 minus e to the F prime minus 1, F prime minus 2. Okay, let's not write it this way. minus, but P was chosen in this way. So 1/3 times n to the e to the f prime over m to f minus plus f prime. This is what you get. But what's this? So using the definition, this is e f prime minus 1 over e f prime times f prime minus 2. This is what you get. Okay. So if you do the computation, yes, this is you get. It cancels out. Yeah. So what you get? 2e of f prime minus f prime over e f prime minus 1, which is what? 2 minus f prime minus 2 over e to the f prime minus 1. So this is 2 minus 1 over m to f. So here, yes, what you get is, this is the exponent that we have computed, 1/7 and to the 2/1, the 2 density. And here you have 1/3 is also no. So 1/3 to the e of f prime, and then e of f prime is like 2. So this is 1/9, and n to the same exponent. The reason how we chose this 2 density, how we defined this 2 density, was to make sure that this number and this number coincide. So that's the motivation on how we define this 2 density and how we define this P. Then what? Then that's like 1/100 times n to the 2 minus 1 over 2 density over. So from here, if it's the average expectation, there must be a choice that's better than the expectation. There exists a choice such that x minus y is bigger than 1/100 and to the 2 minus 1 over m to f. For such a graph, what we do is we delete on h from each copy of f prime, then we obtain a graph with at least 1/100 times e to the 2 minus 1 over m 2 of f edges, having no copy of f prime, hence no copies of f. So this shows what we want. For large n, I mean, this c being 1/100 is enough. For small n, maybe you have to take the c smaller, but this give you what you want. You might be wondering why we take this subgraph instead of the entire graph in here. I mean, one of the reason is that considering this subgraph give you a better constant, better exponent here. For example, in the above expectation computing, when you have a expected number of triangle, then what? It's n cube, n choose 3 times p cube, right? But if you compute this, the expected number of that, then this is what? N choose 3 times p cube times additional n square. The expectation is higher. I mean, the probability that this appear and this appear is same. But once this appear, this is counted only once. But once this appear, it doesn't matter what other two vertices you can take. So as long as you have one, you have n square of them. So the expectation is higher, so that the above computation give you a worse number, because here we only consider about the expectation. So to get the better exponent, it's better to focus on subgraph, which actually matters. The rest of them are sparse, so that as long as you have this, the rest of them are easy to get, and you want to forget that. And then, based on this expectation computing, this give you the motivation for defining this two density. So we have this probabilistic lower bound, which works for all f. But unfortunately, this is not tight. For most of the bipartite graph, this is not tight. For example, this implies that if you have KST, it's give a lower bound of this form. But this is not tight. And there is another approach using algebra to prove a lower bound. But in this case, it sometimes give you a very strong lower bound, but it's taking advantage of specific structure of your graph app. So this applies to only specific graph of app. So, for example, for K22, we can prove the following lower bound, which is, so asymptotic upper bound we proved was r plus little 1 times n to the 1.5. So this determines the asymptotic behavior of K22, extremal number of K22. So how do you do it? So for large n, we only care about large n because we have this little one term. So if n is small, then you can just take this little one term, large number. So as long as this is the function that goes to 0 as n goes to infinity, it's okay. So for large n, we know that there exists a prime number p between 1 minus 0, 1 square root of say n plus 1 and square root of n plus 1. So you now consider the following graph, which is called the polarity graph. So she has the vertex set is you take a field of characteristic p, fp square, then you delete the 0, 0. And H set is between a, b and x, y if ax plus by is 1. Okay? That defines a graph, but more specifically, it gives a multigraph as it could contain loop. There are no multi-edges, but there could be a loop. So we just delete loops if they arise. So for say A comma B and A prime comma B prime, which are not same or distinct vertices. So these are the vertices of G. G, if what? XY is adjacent to both A comma B and A prime comma B prime, then what happens? Let's say this if and only if ax plus by equal 1 and A prime x plus B prime y equal 1. So you have two linear equations. Then it's easy to see that the set of points in P2 satisfying both equations. Let's say the set of points satisfying each equation, let's say, forms a line. And as this A comma B and A prime or B prime are different, those two lines are also distinct. And so what do you know? If you have two lines, the common point contains at most one point. Then the solution that contains at most one point. Hence, there exists at most one common neighbor of this A comma B and A prime comma B prime. This implies that it does not contain any K22. So K22 requires there are two vertex A comma B and A prime comma B prime, and then there should be also two common neighbors. But we just show that there are only one common neighbor, at most one common neighbor, implying G does not contain any K22. And moreover, so this is the K22 free graph. Moreover, we know that every vertex has degree P or P minus 1. Why? I mean, so every line, it's easy to see that every line has P points in it that give you P neighbor. And one of them could be itself. In that case, we deleted the loop. So it could be P or P minus 1. So the total number of edges is at least what? Half times P minus 1 times the number of vertices. How many vertices does it have? P squared minus 1. That's how we define here. That's what? At least half times minus 0 and 1 times n to the 3 over 2. And what? We have P squared minus 1 vertices, which might be smaller than n. Then we add some isolated vertex if necessary to make it n vertex graph. Then this gives us what we want. Okay, so here we use that the line, if you have two lines, the intersection at side at most one. In 1966, Brown proved that the K33, it's the extremal number is at least half minus 0.1 times 10 to the 5 over 3. Roughly what it use is that if you have a sphere, if you have a sphere and then another sphere, then you get this common cycle, right? And then if you have another sphere, third sphere, then what do you get? You have this cycle and then you intersect with the third sphere, then the intersection is at most 2. So 3 sphere, assuming they are distinct, their intersection has at most 2 points. So using this, you consider some like finite field tuples, and then you define your graph based on this equation for sphere, and then you show that once you have 3 vertices, which corresponds to the sphere, their common neighborhood size is at most 2. So it does not contain K33. That's roughly how this proof works. So this more or less determine a asymptotic value of this extreme number of K33. But the extreme number of K44 is not known. Okay, so we have went through 2 ways to obtain the lower bound on the extreme number. One is progressing method, and the other one is algebraic method. And in next video, we will learn more about this, algebraic technique that we can use to obtain lower bound on the extreme number. Okay, thank you for listening. I will see you in the next video then.